Hi all, this is Krishna here. So today in this session, we are going to discuss about uh, the concepts related to the ACR and the DCR testing. So we'll just try to go through the introduction part of it. Okay, what exactly they are, and then we will try to go a bit deep related to EIS, uh, like what is exactly the EIS and how exactly it is conducted on the battery and what could be the scope of it. Okay, and then we'll try to see some ECM systems. Those are nothing but your cell models. So cell models based on your DCR data and the ACR data, we'll try to see, and we will try to discuss in detail about some graph. We call them it as coal plot or Nyquist plot. So, and what all the elements of your ECM model can be matched with your uh, coal plot, that is your Nyquist plot. Okay, so and the elements which we it is involved in the EIS, not EIS, like in the ECM systems, like resistors, capacitors, how they are going to exactly uh, contribute in terms of behavior of the cell. Okay, how we are exactly mimicking that behavior with the electrical system, that will try to match. And at the end, we have some one set of results where we have collected the data from DCIR and the ACR testing machines, and we put into some cell model and we got the voltage response as output. So that we will try to discuss. Okay. Yeah. Okay. We'll move ahead with the session. Okay. Yeah. So about DCIR. Okay. That is it is nothing but your DC current where we are going to use to capture the cell behavior. Okay, so there are different approaches, different profile of DC current can be put or taken out from the cell, so that you will have the different voltage profiles. Okay, so whatever the voltage profile we get from them, we are going to extract our the required parameters. So parameters are nothing but your elements, that is electrical elements. So with that, you can construct your equivalent circuit model. Okay. So here, equivalent circuit model, you can take it as Thevenin. Okay, I'll just try to put some here. So it can not only the Thevenin, it can be anything. You can attach some more RC param, RC blocks. So this is R1, C1, and R2, and you can attach n number of RC. Okay. So this can represent your Thevenin circuit because of one RC pack. So the cell behavior will be captured with these elements, resistors and set of RC blocks. Okay, so you require the data for this one, right? R0, R1, C1. So how they have calculated? So with the help of this DCR testing. So you are going to at some particular conditions, you are going to feed a current profile. So from the current profile, you are going to get some voltage response. Okay. So right now here example, let's say a pulse current has been given, pulse discharge current right now. Okay, this is at one instant, the pulse is been given. So this is the duration of the pulse. You can take it as a T, and this is the value of current. So it means you have like went for like 3C or 2C pulse, like you can take it as like 5 amps or like 10 amps of pulse. So it is given to the battery, and this is your like voltage response of the cell. So from this voltage response, uh, if you take like DCR, we call this as like ohmic resistance, and this we call it as like the where well initially it drops a lot. That is because of ohmic resistance, and slowly like gradually like it stabilized. So this is because of like because of its internal transient behavior, that we can call it as like polarization effect. So even like that is represented with this RC, this R1. Okay. So in this way, like we can capture. So with the help of like Ohm's law, let's say like Ohm's law is nothing but your V is equal to I into R. Okay. So with this, you can like calculate your R0, R1. Okay. And yeah, this is your like the DCIR approach. Then there is like, yeah. So this is for one instant of, like, let's say right now the cell is like at some particular SOC, and you are getting this voltage response when you provide this pulse current. So it is done for different SOCs. So let me take you this thing. Here you can see this is the pulse, the overall pulse, and this is done at like different SOC until from fully charged to completely discharged. Like they will take the cell to the completely discharged. They are going to conduct, and at each SOCs they are going to capture these kind of profiles. And with these profiles, you can like divide your R0, R1, and you can like derive your RC parameters. Okay. So because we know that like R0, R1, C1, like all these are function of SOC and temperature. Okay. Yeah. So this is about like DCR. I just went through in overview. Okay. And with the DCR based the data, right? We can like represent the cell models, like the first order, second order. Okay. Yeah. And there are like third order. You're just increasing the RC blocks. Okay. Yeah. So other than your resistance and capacitor, you won't be seeing any other elements in this like DCR based approach, or like whatever the data we capture from the DCR. Okay. So this is about like DCR. And then there is like ACR. So where we are going to use AC current. We are going to imply the AC current, which will be in a with some particular amplitude, like you can say it is like frequency. Okay. So it will be like sine wave, and you will get some output uh, with a, let's say like you have put the current and the voltage will be the output. Okay. So the potential has a output. So even it appears in some like sine wave, but there will be some difference in phase. Okay. With some phase angle produced. Okay. Right now, like don't worry about this phase angle thing. Yeah. So basically you are applying the AC current at some particular frequency, and you are based on that you are going to like capture your resistance of the cell. Okay. Yeah. So, like we are all this the application you can say usually like these are ACR based testing when we are doing the cell sorting, when we are like conducting end of line testing for the whole battery pack. So you will have the requirements like for this particular cell, what could be the resistance range it should have, or like if you take the battery level when it like taken it for assembly purpose in the vehicle. So and at the end of line testing, you will be conducting these things. So what could be the resistance or range within that it should come. Okay. Otherwise, it will be taken as like odd one, or like it will be considered as odd. Means it will be completely taken out. So yeah, in this way, like at one particular frequency that you can typically generally, as I know, like 1 kilohertz is used. Okay. So at these hertz, they are going to conduct the ACR testing, and you are going to get the resistance, and that will be compared with your requirements. So based on in this way also it can be used as application. So it will be a quick one. Okay. Yeah. So extension for this one. Yeah. Before going, this is some like comparison between DCR and versus ACR. So you can just make a note or something like. So it is just a difference, like where in the DCR we are going to put the DC current and the voltage response what we get. Where from the voltage response we are going to derive all the RC parameters. In the same way, like here for the ACR, and at what particular frequency we are going to feed that AC current and what could be the outputs. The same thing. Yeah. So with this, like understanding basics of the ACI, then there is like EIS. Okay. So EIS in the long form, we can say that like electrochemical impedance spectrum or spectroscopy. So it is a method to capture the battery kinetic behavior. Okay. So at one particular frequency, a sine wave with amplitude is applied to the battery. Sine wave is nothing but your like current itself in the form of like sine wave, and the system generates a sine wave current response with the frequency of at the different frequency. Okay. So whatever you are seeing here, let me put it over here. Just a second. Yeah. So right now, like you are seeing here, like right. So at one some amplitude and at some particular frequency you are feeding, and you will be getting the output signal with some phase difference. If you try to overlap on the input, it may appear like something like this. Okay. Yeah. So it is fine. So here something like we call it as like EI sweep. The word EI sweep. It means conducting like this is like implementing the AC current at some particular frequency and with small amplitude. Okay. Like that is with the frequency itself. So like at different frequencies, let's say like I'll just take some random number like 1 to 1000. Okay. Right now I'm just taking a random number here. So conducting the EIS thing at different frequencies, like at frequency 1, at frequency 2, at frequency 2 or 3. So till 1000. So because like why it is conducted. When you take a cell, right, like it is made up of many materials, right? The like again the electrodes, like like anode, cathode, like again there will be some electrolytes. So there will be like a lot of materials. So all materials property or the behavior cannot be captured at a single frequency. So it has to be like captured them individually. So then you have to like run it for like different frequencies. That we call it as like EI sweep. We're just sweeping, okay, at the different frequencies and tapping out uh, the properties. So the property is nothing but your impedance of the cell and other like capacitance, double A capacitance and Warburg. Okay, so we'll discuss the points. Okay, yeah. So here you can see when we talk in the frequency domain, like we just represent um, the Ohm's law in the different format. You can see over here. So Z is nothing but your impedance. Yeah. So once you conduct this, you are going to get the graph. You can see here. Let me show you. You're going to get this graph. So we call this as an Nyquist plot. So we will discuss this point in the later stages. So I like you understood the EIS thing. So yeah. So just let me know, like, is there any problem in terms of like my voice or something like?
No, Krishna.
Okay. Yeah. So the scope of the AI studies. So what level uh, you can like capture the details related to the cell, that is your transfer of your electrons from current collector to the active materials, and like transfer of electron across your composite electrode, diffusion of ions through your electrolyte, diffusion and migration of ions through a separator. Okay, so if this is your like cell, we used to typically represent the cell in our college days. Similar like anode, cathode, one will be separator and this will be the electrolyte. Okay, so yeah, diffusion of ions in a porous electrodes, double layer charging in the solid electrolyte interface. Okay, so these are some of the like details we can study through the EIS. Okay, so there will be a degradation of your electrode, like because of that you will be able to see the higher uh, resistance. So some like irregular particles or the plating will be happening over the cell, sorry, cell electrodes. So we call it as like lithium plating, you can say. So it is nothing but a SCI layer, that is surface electrode interface. So because of that also the resistance is going to increase, because diffusion of your ions to the electrode becomes kind of, it will give some kind of hindrance. So that will cause in terms of a resistance. Okay, so yeah, in the same way like there are many. Okay, so these can be captured, okay, through the EIS. Yes, so at our office like we have a machine like this. It is like BT 44560. So it is a range is from 0.1 hertz to 1050 hertz. Okay, So within this range, like what all things can be captured. So that we are going to see in the next part. Okay. Yeah. Let me take you there. So yes. Yeah. This is about like what you say, the types of tests. One is like potentiostatic and galvanostatic. So here we were discussing about like input, like either with the potential or the current, we are going to see the output either with the current or the potential. So here the potentiostatic itself says that like a method of measuring the impedance by controlling the input potential and the output current is measured. So you're going to feed the potential and you are going to get current as output. That we call it as like potentiostatic. In the galvano, like you are going to feed the current as an input and the resulting is your potential. That is going to be the measure. So here, like when you want to capture the low impedance systems, so at such cases, this is used, the potentiostatic. Okay. And like they are very sensitive to the small changes in the input response. And like the systems which are like very less sensitive to the small changes in input current. So where those for such systems like galvanostatic approach is used. Okay. Yeah. So with the equivalent, sorry, with the like EIS based data, like how we can represent the ECM. So you can see over here, that is like the same ECM model you are going to see, but along with your resistor and capacitor, you are going to see some extra elements. Those are like inductor and the Warburg. So you are going to see the inductor behavior of the cell and the Warburg as an additional like a resistance is added. So that is completely related to the diffusion of your ions part. Yeah, that we'll see. Okay. So here, uh, let's take this graph itself. So it will be easy to understand. So here I have like mentioned some equivalent circuit model and the respective Nyquist plot. So this one is referring over here. This whole thing will be referred to this semicircle, and this one will be referred to this semicircle, and Warburg is refers to this like a flat line which is at some particular angle. That angle is nothing but a 45-degree. Okay. Yeah. So you take any like cells which is of like lithium ion technology, or like especially I have worked on the NMCs more compared to the other. So we see this kind of graph, like either like one circle or like sometimes like two semicircles. Okay. So this is semicircle refers to some like RC block. So that you can see over here. So what exactly like these are? So we'll just try to see them. Here, like the element wise description I have given, like the resistors we are going to use. So what exactly it represent? So the resistor can be, this element can be used to represent your ohmic resistance, like ionic resistance of your electrolyte, SCI resistance, charge transfer resistance, which is between the electrolyte and electrode. And the electrode, yeah, and the inductor. The inductor can be represented the impedance contribution related to the battery structure at high frequencies. Okay. and the capacitor, the charge accumulation or depletion occurring at the electrical double layer between electrode and electrolyte. So the capacitance, like how what is the capacitance, right? So, and then like constant phase element, uh, we can represent with the CPE as in annotation form, and it is used to match the deviation of the frequency response characteristics of an actual electrode from a pure capacitor due to the dispersion phenomenon. So, like I'll just go through them. So these are some of the elements will be representing your uh, cell model. Okay, like which is used in a cell model, and those mimics your like real-time cell behavior. Yeah. So yeah, now here comes the main graph. So when you try to conduct the EI sweep for a particular cell at like from 0.01 hertz to like 5 kilohertz or like 10 kilohertz, so you will be able to see the whole graph. Yeah. So this graph is like one with imaginary and one with the real time. Okay. So here the red one you are seeing that represent your inductive behavior of your cell. And this particular point represent your like ohmic resistance. And this first semicircle represents your resistance of your SCI, that is surface electrode interface. And the next circle represents your like charge transfer process. And then whatever the line which you are seeing, it is like straight at some particular angle, inclined at some particular angle. So that we call it as like walk bar. Okay. Yeah. So here you can see we just like represented in a description manner. So here a general way of representing the frequency range, mid to high frequency. So for these frequency range, these all can be captured. Okay. Yeah. All these elements can be captured. So this has to be like conducted for the cell at the different SOC so that like you will have the data with a function of SOC and even the temperature also. So these are some metals data. Okay, I'll just pass through. Yes. So here, like R naught, whatever we are seeing is the resistance induced by internal materials, that is your active materials and the current collector. This ACIR, the resistance induced by the passive layer on the anode due to the electrolyte decomposition. So what exactly like ACI, right? So when you take some electrode, right? When you first going to charge or discharge thing you are going to do on the cell, it will start with the formation of some layer, a deposition of some layer on the electrode. It cannot be seen. Okay, I'm just trying to mention it over here so that you can get a thing. So this layer over the period, it is going to increase the width of this layer. So this offers a resistance. Okay. Yeah. So that layer we call it as like surface electrode interface. This one R naught is nothing but your resistance offered by your like electrolyte solution resistance, your separator. Okay, so like when you take two electrodes, when you try to charge or discharge, so electrons will be flowing through your external circuit, where ions will be flowing through your electrolyte. So these ions movement will have some resistance within the electrolyte, that is your solution, and like maybe the separator or something like that. So even that resistance we can call it as like R naught. Okay, and then the charge transfer. So that is between the two electrodes. Let's say like here the ions are there, and those has to get deposited on the electrode, right? So there will be some resistance offered by the electrode. So that we call it as a charge transfer. And then the final resistance, that is your like dip, diffusion of your lithium ions. Due to the diffusion of your lithium ions into the solid active material, that is your and like your electrode itself. So because of that, some more resistance is offered, that we represented with the Warburg element. Yeah. So this is about like understanding the elements. So what exactly we do, right? So when you like put up this graph, so this is for one particular instance of SOC, or maybe like one particular instance of a temperature. So when you try to like conduct this EIS for different SOCs, you will get the difference in the graph. For example, so let's say it may appear like this. It doesn't like overlap. Okay. So, like the cell is very stable and very less resistance when its operating range is between like around more than like 20-30% of SOC and less than like 90% SOC. That is like more stable, and where you see less resistance at the cell. When you try to operate at lower SOC, you will see the higher resistance. So the length of these graphs. So right now, like this is the length for the RCT. This is the length for your what you say RS, that is nothing but your SCI layer. So even the length of these graphs is going to change at the different SOCs and at the different cycle of the cell. Okay, so though those also represents your the degradation of your cell. Okay, higher the length, higher this width of this, or like length of this semicircle indicates the cell has been degraded, something like that. Okay, so yeah. So in this way, like the testing is conducted at different SOCs at different temperatures, and you can like use those data to plot them. Okay, so if you go for DCIR, right? Okay, let me, yeah, you can see some like Ohm's law equation, and you can like draw it or draw the data. So from like Nyquist plot, like how you can like draw all these RC parameters. So there are like a lot of equations, and the equations are like very complex. So don't worry about the equations. So there are some like built-in applications where through the curve fitting approach is being used. So with that, you can like capture this RC parameters. So one of them is like circuit fitting. So you can just put up the results and then you can like capture it. So we'll just try to perform one of that part. Okay. So yeah, just give me a second. So I'll just try to open one circuit. So this is one of from the IoT itself. So whatever the data we have, we are going to fit for this particular electrical system. Okay, let me select my impedance data. So I have them somewhere over here. Let me check. So I'll just randomly select some data. I'll just take this one. So I have already, I have this data in a Excel sheet format that is like .csv. I'm going to select this file, say open. So it will take some minutes to open. Like some minutes, okay. Yeah, I think it happened quickly. So you can like refit it if you are not satisfied with the fitting with the original profile. Okay, so here you can see the data, right? So R not R3, R1. Okay, so these data can be taken like so this fitting, like first you have to collect that particular CSV profile at the different SOCs, and then you have to bring it somewhere like this applications. So there is a ZWeave that is also one of the application. You can use that also. So right now this is open source, so you can use it. So circuit fitting. So conduct this for every like SOC and what all SOCs you have captured, right? Like EIS has been done. So collect all them, collect all of the data and conduct this EIS for every SOC and take this data. Okay, and then you can use them in the cell model. Okay, yeah. So this is like approach, and yeah, we show. Uh, so here you can see like we conducted for one particular cell at different SOCs, like SOC 0, 5, 10, 15, 20, 25. Okay. So this is the graph we got. Let's see for the 100%. So this is the graph. So our machine has some limitation, that is it can go from 0.1 hertz to like 1050 hertz, that is 1050. We can't go for like further, okay, because of the limitation. Yeah, the machine itself has limitation. So yes, so this is the same cell, like one particular cell and conducted at 100 SOC. In the similar way, we take it for different SOCs, and you will be going to see the difference in the graph when we try to overlap all the graphs. Okay. So yes, at lower SOC, you can see the graph, how it appears. Yeah. So like, so in this way, like you can like conduct the studies through the EIS approach, and we got to know like what all things can be learned through that machine. Okay, the EIS machine. So let me go to the slide over here. Yes. So this is like one of the machine here. So you can capture. So you can see from this graph, sorry, yeah, from this graph, like at the different SOCs, and when we try to overlap, you can see the graph, like how it appeared, right? Yes. So these length, the width of these semicircles defines your resistance actually. So I am not going to like uh, bring that topic over here. So it is like again lot of discussion actually. Yeah, and it's a complex one. Yeah. Yes. So till now, like I have given some introduction to the EIS part, like ACR and EIS part, and some part related to the like profiles, what kind of results you are going to get and what that result represents. Okay, and what all, uh, whatever the results we got, how we can match with our cell model. Okay, with these elements, we got to know. Yes. So these are some of the results, or like this is the output results of our model. So you can we just put it for the comparison. So Randall circuit. So we call it as like Randall circuits. When we try to include the Warburg and the inductor, then we call it as like Randall circuits. So again, in the Randall 1RC, 2RC, you can like try to see the results data here. Okay. So Randall's 1RC model and the test data. This is the real-time test and this is the Randall's. So almost like less than 2-3% of error, like less than 5% error, we have like captured the exact voltage response. Okay, don't worry about the last part. You can like take up to like 3 itself, so you can see. Yep. So these are some model results, like which we captured.